This talk has the title Design and Experimental Evaluation of an ESP32-based power quality analyzer with introduction to supraharmonic analysis. The speaker is Axel Martinez Jacobo, please.
Hi, good afternoon. My name is Martin Jacobo. My topic is design and experimental evaluation on the ESP32 based on power quality analyzer by introduction to superharmonics analysis. My outline is introduction first, second materials and methods and materials, and third, device fabrication. Fourth is experimental. Um, a little background. It's by conclusion. Introduction. The harmonics electric generated by Chargard's electric no line. For example, variable frequency drivers for modulation or commutation. UPS. I use the UPS for a fast charger device. This is new problem for harmonics because generate high superharmonics and interharmonics. I use the discrete time Fourier transform because I have the same in the time. I need the same in the frequency. I mean, I need others equations. It's very important. The percent. The percent, the total harmonic distortion. For example, the equation does, I use for a voltage distortion. The distortion, the measurement is it's this one. For example, V1 is the magnitude fundamental, 60 Hz. For example, V2, V3, V4, V5, V6 is the magnitude of the harmonic, numeric, the harmonic voltage in voltage, the magnitude and voltage. Another equation is for current. The current is same. The current one is the magnitude fundamental current, 16 Hz. And E1, E2, E3, E4, EM is the magnitude, the harmonic current. This is the diagram of the prototype connections. I use the ESP32 and Raspberry 2014. Well, I use the Raspberry for environment sensor modules, for example, temperature, pressure, humidity, others. And GPS for the time. Materials and methods and materials. I use the voltage sensors. I use the length model ELA22P. This sensor have a accuracy 1% ish. Is a high accuracy. This is the model. The nominal voltage is this one. And it calculate RF for need 10 milliamperes. Because this is a transducer, I think magnetic fields, later a current, finally voltage for ESP32. And the current sensor, is this one. And nominal current is 13 amperes. At the same area, because they need a nominal voltage, one voltage, because the primary current nominal primary is 30 amperes. The secondary is 15 milliamperes. 15 milliamperes for because one volt. And this one is my prototype. This one, the voltage sensor modules, and the current sensor modules, and the environment sensor modules, and the GPS, and the micro SD system, and my system battery. I use the battery lithium, the model 16A15. Firstly, I need the sensor calibration. My step voltage is this one, is 22, 42. Okay. And the current step. Finally, I have the sensibility of the sensor, the current of the voltage or voltage. This one is the sensor calibration curve with offset, because the ESP32 no read negative voltage. And current sensor curve with offset. The nominal current, and negative nominal current. I use the for calibration the source totals. This one source have a I don't see a very high accuracy, is this 0.05%. Is very good current accuracy. This one, the voltage, I don't see, is and the total harmonic distortion. This source have a synthetic harmonics. I realized 5 tests. One test is simple. Technical simple. This two is harmonics generated by incandescent lamps. Is 3, 5, and 7 harmonics. Test 3 generated by LED luminary, generated by fundamental 100 volts element, and 5 and 7. And 4 is generated by switched mode or power from computer chip and others. This one is 3, 5, and 7 harmonics. This 5. And finally, this is a special test because the source tokens have a 18 number of harmonics. Is considered the superharmonics. This is my third one. The single in time domain. And my single in the spectrum. Is my test 2, my test 3, my test 4, and the mind and time. And test 2 and test 4, the mind and the spectrum. And my final test. And well, it's a special test because I have a harmonics, a super harmonics. And real conditional test. I have a wired motor. And this one motor driver generates a super harmonics in the input and output. And input generate algebraic harmonics classics because no, in the motor drive output generate super harmonics, especially in voltage. The motor drive connected a motor. The motor connected a generator. The generator connected for a resistor bank. And the prototype connected a motor drive in input and output. And this one pictures. I have the all cell. At primary energy source, where the motor, the drive, the prototype, and a commercial equipment. This is a power pod by a motor and generator, and the resistance bank and source force. The motor connected by generator for a poly system connecting from the motor to generator. My prototype connect a motor drive, then input and output in nominal charge. And nominal charge. This one is a commercial kit. And my prototype. This one is I have waveforms in input. This one is a voltage, and this one is a current. And output, this one is a current, and this one is a voltage. And time domain. And this one is my waveform for my prototype. This one is my voltage, and this one is my current. And in input of the motor drive. Later, output the motor drive. This one is a current voltage. This one's a current. This voltage.
You have 2 minutes.
And this picture, I have two where height form of the voltage and the current in time domain because the super harmonics and this one with THD for my prototype in ESP32. This one is calculate. This one is calculate for my lab. My prototype have a capacity for view 1 1,500 harmonics-ish. The commercial IT only have the 15 harmonics. For standard AAA, 1,015. 19, pardon. For my conclusion, my prototype compare present is significant beyond the 100 tenured harmonics. And I have a GPS and sensor environment. My reference. Thanks for attention.
Thank you very much. So we thank the speaker. And we have time for several questions. Any question?
What is the purpose to use discrete time Fourier transform instead of the fast Fourier transform? American, or what is the main purpose? Because the fast Fourier transform is faster by definition in American.
The frequency?
No, not the Fourier transform. You mentioned that you are using discrete time Fourier transform, but this is not as effective as the fast Fourier transform. Your term is like
this. Because I need the magnitude for spectrum dominion for the magnitude of the voltage or the current. This one is 16 hertz. 1,000 plus the multiplier is 16 hertz. 2 is 1,020 hertz. 3, 1,018 hertz. I need the magnitude in this one specific frequency. For example, this one is 18 voltage. And the magnitude in this one frequency number 1, 16 hertz, is 18 voltage.
Any other question? I have two, actually. Well, I wonder about the calibration of your sensors. What I mean, it is due because of the circuit you are putting them in, and then you have to calibrate, or is there not a calibration provided by the supplier?
No, I use the source couples. The accuracy is very high, very high. It's 0.05% ish. And this one is my pattern. And my steps for calibration is this one. And nominal current, and nominal voltage. And my minimum validity.
Okay. And the other is as a load, you are using a resistance bank. Why not to consider some other load that can really imply also harmonic creations?
The harmonic creation generated by this one, the drive.
Yeah, but then that's in the, how to say, like the input to the system. But you can also have harmonics coming from the output of the system, that is the load. In this case, you have a resistance bank, but you have something like really influence the frequency of the signal that is the output.
No.
And you also can have harmonics on that side.
No, not generate. The resistance will not generate.
No, the resistance no, but why not to do some experiments with some other load that can generate also harmonics on that side? Like inverter, rectifiers, and so on. Like to check all the system.
there are harmonics generated by Rai motor because have a switch, source switch,
A switching. Yeah. Well,
and and generated by the harmonics all time, because the generate for the source switch.
is there any other question? Well, we are done. We thank you once more. So our next talk is online. I think Tarek Berhout is already connected. Please, can you put presentation? Thank you. Let's and get what? Okay, the second talk of this session has the title Deep Learning and Machine Life, a critical empirical perspective, introducing phase shift degradation analysis in prognostics. And the speaker, Tarek Berhout. Sorry for the pronunciation. I have no idea. It was already connected. Okay.
This great
Can you
event.
share your
First
screen, please?
Yes, I am sharing my screen. Do you see it?
Not yet. There, yeah. There's not.
Yeah.
Okay, perfect. It's just about doing it. No, it says it's finished. The share contents.
Do you see my presentation?
No, we see the assistance chart.
لا حيدر ما بغيت شي. What about now? Do you see my PDF file?
Yes, now it is.
Can I start?
Can you put full screen, please?
I'm afraid
screen
that we lost the sharing if I did so.
Okay, then do it. Then do it now.
What about now?
So,
do you see the full screen?
it's okay. You can present. Yeah. Yeah.
Okay, thank you.
You're working.
So first of all, I would like the CCE organizers for this great event. I have participated last year in this event, and I am happy for other contribution this year. Thank you all for organizing this excellent event. First of all, I will introduce myself. My name is Tarek Berhout. I am from Algeria. I work at the University of Batna 2. I'm holding a position of Chief Laboratory Technician currently. In my free time, I do research, mostly about artificial intelligence techniques. I use artificial intelligence as I started in my PhD in predictive maintenance. Then I worked on many fields like bioinformatics, material science engineering, and cybersecurity, and so on. Today, I'm going to present to you a new topic that I'm hoping to introduce as a new topic in the field of predictive maintenance, more specifically in prognostics and health management, meaning early prediction and early diagnosis of events in industrial systems. So the presentation titled Deep Learning and Machine Life, a critical empirical perspective, introducing phase shift degradation analysis in prognostics. So traditional prognostic systems, when they try to build data-driven models or machine learning models or whatever deep learning models, they consider the system is degraded gradually. They never consider the fact that the system can be in a stable mode or in recovery mode due to some control systems, integrated control systems, or perhaps the resilience of the system itself. So when they build machine learning models, they consider that in data processing, they consider that should find a way to process data to prove that data is in a monotonic way, meaning that the sensors measurement of the system in an entire life cycle, they should present some kind of gradual deterioration. And they ignored this fact of possible recovery of the system due to control or maybe due to resilience itself. So in this presentation, what we are trying to introduce here is we are trying to make some simple experiment on in classical degradation analysis, and then two different cases of stabilization, which we named thereafter a plateau, and then a plateau with recovery, meaning the system recovered from degradation states to at certain in certain period, then it continues to deteriorate as in classic deterioration. So we made a comparative analysis also between machine learning, meaning small scale mathematical models or training models, and deep learning models. We use the tool LSTM, long short-term memory, which is very known in the field of deep learning for time sequential analysis. The goal from comparing deep learning and machine learning model is to show that if deep learning models truly follows the degradation process or not compared to linear regression models, because deep learning have the ability to learn more complex patterns, and when learns more complex patterns and incorrect labeling process, meaning that it will stuck in inaccurate prediction and certain predictions. So after that, after the comparison and the showing the result, we'll end up with the conclusion, an important conclusion, which opens a new door for prognostic and health management systems. And then we ended up with very important perspective and future pathway in this field. So in this figure here, present the different cases, the classical degradation here in the first subplot, and then a degradation with a plateau, meaning stability, a kind of stability of the system. Maybe the system in this phase tries to recover or tries to be resilient to, and also maybe the control systems here trying to make the system stable even under harsh conditional environment. And then the system continues to deteriorate accordingly, like in traditional linear degradation systems. In the third case scenario, it's a kind of hybrid between these two cases. It's a case of degradation and then a kind of stability, and a third probable possible recovery system, a complete recovery from unhealthy deterioration patterns for a moment, and then finally the system continues to deteriorate accordingly. So we will base our study on these three datasets. By the way, these three datasets are synthetically generated based on mathematical assumption, but we did our best to add noise and add some fluctuation in data to imitate realistic case scenarios as in real industrial systems. And also, we made the data as complex as possible to be, meaning to have the ability to apply both deep learning and small-scale machine learning. So here in this figure here in this slide, we see our defined deep learning models. So we introduce basically a single LSTM layer with, of course, a fully connected layer that is linked to regression values, meaning one single output neuron for health index, or probably in reality it can represent, for example, remaining useful life, or maybe state of health or state of charge, and so on, depending on the system. In the LSTM layer, we used 15 neurons and specific parameters to make sure that the deep learning model can reach its maximum accuracy in these three case scenarios. After defining the LSTM, we not forget that we used a linear regression model as a reference to compare also LSTM, because small-scale machine learning have not the ability, same as the deep learning model, to learn complex patterns. So generally, long-term memory in complex environment automatically will achieve better results. By saying better results, meaning better training. But in this case, better training can lead to overfitting and misinterpretation of our results. And this is what we are going to prove later in our results. So this is the first case with the linear regression model. See, in the predictions of course in generalization, we use the 80-20% split data set and we train our model. In this figure here, we show results of generalization, meaning training on an unseen data samples. In the linear degradation process, the linear regression model works perfectly. In the other cases of recovery, we see that the linear model imitates the same path of those two cases. The same conclusion here are applied for using deep learning model, but visually we can't see the difference. So we need another experiment that can show us the difference between long short-term memory and simple linear regression model. So we used evaluation metrics like like for example, mean absolute error, mean squared error, R squared, and so on. What we can see from the results here, in all the three case scenarios, that the linear regression model shows better approximation results and in generalization results than the LSTM. The question here is why the linear regression model is able or was able to show better results. In this case, because there are ground truth labels that are incorrectly represent the plateau case of stability and also the case of recovery, meaning if we want to obtain better accurate results, either we should modify the ground truth or we found another way to filter those misrepresented data or misrepresented measurement to provide better results. So in this case here, LSTM is based on linear regression, of course, are based on mislabeled information. The mislabeled information, and due to the fact that LSTM can learn better or learn in a better way, a very complex pattern, makes the LSTM model achieves or stuck in the problem of overfitting. And this is why the linear regression model obtained better generalized results. So in this case, we suggested two important solutions. As a solution, we need to try at least this theory of both horizontal and vertical training or filtering of our dataset. Either we filter the dataset and remove that mislabeled information, or we relabel the ground truth based on the real behavior of the system during the degradation path. So one of the solutions is to filter. If we want to filter or to remove these misinterpreted results, we can follow this horizontal prognostic path. So we remove the misinterpreted label and consider them that belongs to another phase, for example, healthy phase or stabilization phase, rather than a degradation phase. For example, if we see this figure here, these green dots here are presented as deteriorated pattern, where in fact they belong to a healthy stage. So one is to correct our model, we need to consider this fact. Another solution is to relabel. So we not consider that the system completely linearly deteriorating. So we consider those facts. Maybe we derive the ground truth itself from the behavior of the life cycles, and then we update more accurate labels, and then we can train our machine learning models. So as a conclusion, this work we try to use a new prognostics and health management, which we call phase shift degradation analysis. Considers two cases. Case is stabilization in degradation process and possible recovery, and maybe there will be other cases. This is just an example here in this conference paper to prove that there is a mislabeling during considering training process of a machine learning model in classical prognostic systems. So as a perspective, we suggested two solutions. Either we filter the data set from this misrepresented ground truth, or we relabel the ground truth itself to obtain a better accurate representation. And thank you very much for your listening.
Okay, thank you very much. So we thank the speaker.
Thank
We
you
have
so much.
time for questions. Well, is there any question from the audience? No, I have one. I mean, if from the data you show us, it's clear that the system doesn't behave really linear, precisely in this plateau condition, or when you had even improvement on the health. Why not to use a kind of switching model according to this, I don't know, a triggering event that detects these changes?
Excuse me, switching between what?
I mean, it seems like the data sets you show, they show obviously non-monotonic behavior, yeah? But at the end, you try to fit this data with a model. Why not to use a switching model? Like a model for degradation, a model for plateau, a model for recovery, and then switch
Yes.
between modes. Why?
Yes,
Would it
but
work?
in the realistic case scenarios, we don't know the behavior of the system that we can't guess the behavior of the system itself. So, as you said, it's a great idea that you train our model on many possible cycles. We train our model on linear degradation and other cases, and then the model will be able to generalize on all the cases. This is a great solution, but when we train many models and we switch between them, we don't have the criteria, and there is no way to predict which model we are going to use in a specific health state of a system.
Okay. Well,
Thank you.
thank you. So if there
Thank
is
you so
not any other question from the audience, so we thank finally the speaker. Thank you very much.
Thank you so much. Excellent conference.
That's a good night there, I think.
Yeah, in Algeria, yes, it's a night.
Yeah. Okay. Thank you very much.
Thank you so much, sir.
So we have the speaker for the next talk is connected. Okay. We have 3 minutes time before the schedule, so coffee time.
Excuse me, sir, who is the next one?
Perfecto. Está. Ya tiene su cámara, ¿verdad? Okay, to continue with the schedule, we have the presentation that is entitled Quantum Enhanced Sliding Mode Control for Robust and High Performance Industrial Robotic Manipulation. The speaker, Mehdi Fasilat. Can you hear us?
Hello?
Hi, can you hear us? Yep.
Hello, everyone.
Hi. Okay, you can start.
Can I come through?
Yep.
Could you hear me perfectly?
Yes, we can hear you well. Yes.
Yes, perfect.
We can see your presentation as well.
Yes. Hi, everyone. My name is Mehdi Fazilat, and I'm presenting this work together with Professor Najed Zvi, my director in my PhD student program from University of Quebec at Trois-Rivières. The title of the research that today we're gonna talk about this one is a quantum enhanced sliding mode control for robust and high performance industrial robotics manipulation. We're glad to have an opportunity to present this research in international conference on electrical engineering and computation science and atomic control. Over the next few minutes, I will show you how quantum-inspired algorithms and idea can make a robotics control systems more precise, smoother, and more energy efficient. So start with the motivation. Industrial robotics manipulator usually have to deal with the nonlinear dynamics and external disturbances and lots of parameter uncertainty. And the traditional control algorithm, like a sliding mode control, is great in terms of the robustness, but still have a couple of the big issues. For example, the first one is the chattering effects, and the second one is a high computational load for calculation, the strategies, and control. Now, today's demand for high precision and energy efficient robotic control, the classical sliding mode control should be upgraded for the precise and avoid chattering during the task execution. So that brings us for the problem statement. How can we design a controller robust, precise, and lightweight in computation, especially for high degree of the freedom robotics manipulation? And finally, can quantum-inspired computation help to improve the sliding mode control for performance in dynamic and uncertain environments? All right, so before going to the control design, let's quickly look at the basic dynamic model of the manipulator robotics arm. The purpose is here to describe how motion, forces, torques is related to the general dynamics equation, as you can see. In simple way, the first term of this equation shows how mass and inertia resist about the motion. The second one represents the energy lost and the dynamic coupling, and the third one is the torque needed for against the gravity forces, and finally we can calculate the torque the actuator needed for any motion. The key takeaway is the equation is a foundation of the both controller that we are talking about this presentation. Classical model of the sliding mode control and the quantum version of this sliding mode control. Now let's take a quick look at the classical type of sliding mode control. This is the robust nonlinear control techniques that used widely in complex systems, especially in robotics. And the main idea is pretty simple. It forces the system trajectory between and stay between sliding surfaces so that surface can control, ensure stability and reject disturbances as really well in some tasks. The control principle is shown here. The defined sliding variable with the tracking error and the derivative. When the sliding variable goes to the zero, it means that basically the robot's actual trajectory perfectly stay on desired trajectory that we designed for the manipulation. But the classical sliding mode controls comes with some shortage. First, suffer from the chattering. Second, from the computational heaviness. And finally, it's not very energy efficient in some cases. For example, and especially in complex and high degree of the freedom that we define as a system for a sliding mode control. Now you can see an overall framework of the sliding mode control that we employed in our research for control manipulation of the robots. Has three main parameters: trajectory and trajectory plant, control plant, and also the dynamic of the robot as a general plant. So overall, this setup shows how to reference motion, control law, and the robot dynamics interact in the real times in same time together. Now here, things get a bit more interesting because we're gonna start talking about some quantum concepts. The main motivation, they're using the quantum ideas to integrate with the control strategy, using some abilities of the quantum computing, like a superposition and parallel computing, which basically means that that provide the ability for systems to handle multiple control states at the same time. And the abilities that permits more adaptive and parallel decision-making for robotic systems, which is super useful for trying to control and execute some difficult task for some robotics arm. Opposite of the classical bit that we use in the classical computer, it has just two states, 0 and 1. Qubit in quantum approach can have any state between 0 and 1, and it means has some ability to handle many states in the same time. This is one of the great benefits of the quantum computing. Then we use some other quantum operation that we name quantum gates to perform things like addition, subtraction, comparison inside the control loop. And also this approach give us three main advantages. First, less chattering, faster response, and the third one is a low energy consumption. The idea for the main idea for using this method to enhance the classical sliding mode control by integration the quantum concepts, better robustness and precision and energy efficiency. And basically the framework combines the classical sliding mode laws with the quantum logic error computation. And so the first step for the computing the tracking error, that means the difference between the desired position and the actual position that robots done in the working space. The tracking error equation encoded by the quantum states and using two famous algorithm in the quantum computing, quantum subtractor and quantum comparator. This is the starting point for the rest of the controller that we want, that we are designed. And in the next step, second step, is to define the sliding surface, the quantum version of the sliding surface, defined as an equation that you can see, and using the quantum adder. In the final steps, step number 3, we implement the sliding surfaces that we design into the main control law. So you can see the structure of the equation stay identical for both algorithms, which the classical one, but handled with the quantum principles. The big benefit is a small change in the equation and brings a smoother and chattering-free results for us. This is the overall framework for the quantum sliding mode control. Is very pretty same with the classical one. It has some very main sections, as you can see: trajectory plan, tracking error, and sliding surfaces, and also the same robot dynamic model that we used in the classical one. So overall, this framework keeps the same architecture as the classical version, but introduce the quantum layers inside of the control strategy. For implementation and validation, we use the real robot ABB IRB 140. Is a 6 degree of the freedom, is available in the mechatronics laboratory in University of Quebec. And we use the original configuration because of we need some results comparable with the standard industrial settings. And in terms of the modeling, the dynamic equation derived by using the Euler-Lagrange methods. And also for the trajectories, we define the fifth order polynomial equation for the smooth and stable motion. And also the very important step of this research, we developed a CAD model in SolidWorks. But why? Because we need to extract the mass and inertia properties from the mass properties of the SolidWorks to implement in the dynamical model. You can see in the table the inertia and the center of the mass that extracted, generated by SolidWorks. And honestly, it's not the same with the real data in the real robot, but we tried to use the real geometry for accurate parameter identification to ensure the controller execute their task very precise.
You have 2 minutes left.
Oh. These values that extract used in the controller that we provided. And also for the simulation setup, we execute the circular path for both controllers. And with the same initial conditions, and the start point is the same. The tracking error is beginning. As you can see, the tracking error, the both controller has a tracking error, but the quantum controller conversion is a bit faster. And also, in our research, we introduced the non-stationary actuator disturbances for evaluate the robustness of the robots and controllers. And let's go to the results, because we don't have enough time. We examined many important performance for the tracking for the robots controller, tracking performance, quantum controller achieve a smoother motion and faster conversions. And in other hand, the classical one present a small oscillation, but the delay when the disturbances applied. But anyway, in overall, the quantum controller have a present the very good performance compared than the classical one. All the data for the tracking error average in the 21 independent runs, and you can see the quantum controller have a better performance even with the disturbances in face of the disturbances, and also for the control effort, as you can see, the red one for the quantum controller and the blue one for the classical one. And it's very clear as you can see in the figure and the plot, the quantum controller has a more chattering reduced in the execution during the execution the tasks. And also the other metrics we consider is the energy consuming for both controller during the same task. And overall quantum controller about 3% reduction, has a 3% reduction in total energy consumption. And the other things that we can address is a conclusion. This research introduced a proposed control strategy developed for a high degree of the freedom. A robotics arm, the proposed controller achieved a smoother tracking and reduced the chattering. And also the result confirmed the robust performance under non-stationary actuator disturbances. The quantum controller works better than the sliding mode controller, classical one. And of course, there is some limitation, like this study focused on the first 3 joints of these robots that correspond for the position, not orientation. And also, all the algorithms present for the quantum version is a hybrid algorithm and not yet through the physical quantum hardware. And for the future work, we plan to extend the controller to implement for all 6 joints of these robots and combine and integrate the advanced optimization algorithm like a quantum particle swarm optimization for the gain tuning. And the next one, the last one, is explore reinforcement learning with the quantum control for more improved performances. Overall, this direction is toward the powerful control framework that's integrate the quantum computing and the advanced control theory for more intelligent, precise, and energy efficient systems. Before closing, I would like to thank and acknowledgement to the support from the Natural Science of the Engineering Research Council of the Canada, and the special thanks for Mechatronics Laboratory in the University of Quebec during this research. And I would like to thank to organizers for CCE conference for this opportunity to share our work. And once again, thank you very much for your attention, and I will be happy if there is any questions to answer.
We thank the speaker. We have time for a very short question. Is there any question from audience? Short one. Just one. How efficient is this kind of emulating these quantum gates or quantum process algebra compared to a real quantum computer? I mean, they are It's
Yes.
extremely expensive at this moment. But how efficient is this comparison, this simulation?
Excuse me, could you please repeat again?
Yeah, it's like you are emulating these quantum gates
Okay.
instead of using the really quantum hardware. But I
Yeah.
was wondering how efficient is this emulation based on time and computational effort compared to a real quantum computer?
Yes, it will be, there is many difference because the quantum computers system and structure is a high powerful than the classical one. But already in the current steps, we don't have full access to quantum hardware, but we used some provided platform like ABM Qiskit from the ABM and Penny from the D-Wave, and we translate our classical algorithm to the manuscript and the script that this framework can understand and run on the cloud system. But anyway, with this all limitation, we have a very interesting results that the time consuming and efficient calculation process, and there is a lots of saving in time and decrease the computational load compared to the classical method.
Okay, well, we thank the speaker. Thank you very much for this presentation. And then we move to the next talk. It's Arslan Salim.
Yes, just allow me a minute to share my screen.
Yes, please. Well, I will introduce in the meantime. Well, the next presentation has the title Design of a Solar Photovoltaic Coupled Ground Source Heat Pump for a Small Residential Community. The speaker, sorry for the pronunciation, Arslan Salem.
Should I begin? Can you see
now
my
we
screen?
Can see already your screen, so you can start.
Okay. As you introduced the topic, the paper that I'm going to present today is Design of a Solar Photovoltaic Coupled Ground Source Heat Pump for a Small Residential Community. My name is Arslan Salim, and I'm working as a research associate at School of Engineering, Cardiff University, Wales. And this paper was co-written by Carlos Ugulde. So I'll begin with the outline of the presentation. First, a little bit of motivation, and then the system configuration that it was investigated. Then we'll look into the details of site selection and modeling method. And finally, we'll go through the results, limitations, and scope of future work and conclusions. So beginning with the motivation, we know that globally building stock is responsible for nearly 30% of total energy use and a quarter of energy-related CO2 emissions. And in the context of UK, United Kingdom, decarbonizing heat is critical since the residential space heating, cooling, and hot water combined thermal demand accounts for up to 60% of UK household energy use, which makes it crucial for achieving the net zero target. So looking at the solutions, ground source heat pumps provide a high efficiency, low carbon alternative, but they come with a problem. Their long-term operation can result into ground thermal imbalance, which limits their widespread adoption. So to resolve this issue, the hybrid model, which basically couples the PVT system with ground source heat pumps units, can enhance the sustainability by recharging the ground with solar heat and supplying the additional electricity which can be used to run the energy system, providing further grid flexibility. So here is the schematic of the energy system which was investigated. So if I can. So it consists of 3 loops. The first loop is the PVT loop, which is coupled with the ground source with the borehole heat exchanger or ground heat exchanger loop through a flat plate heat exchanger. And then the ground heat exchanger acts as the source side of the heat pump, which is used to meet the thermal demand of the residential house. So in this case, the residential house that is assumed in this work is a 3-bedroom terraced house, and an actual model of a model of an actual 3-bedroom terraced house located in Cardiff was modeled for this study, and the thermal load of that model building was calculated to meet the hot water demand, space heating demand, and space cooling demand. So moving forward, for the site selection of the boreholes, British Geological Survey was used. This site has the data sets of all the boreholes in the country. So looking at, we basically gathered the information of all the boreholes in the region. This particular work focused on Neathport Talbot area. So in the Neathport Talbot area, around 200 sites with 30-meter depth were narrowed down within the 10-kilometer radius. And the screening method was involved basically ensuring that there is no moving groundwater in the subsurface, and there is no historical record of coal mining. And furthermore, the site or the borehole that is being investigated isn't declared as a site of national heritage. So this was done to basically get the soil properties like thermal capacity and thickness of the material and the properties of the soil layers itself to calculate the thermal resistance. So for the mathematical model, simplified empirical models were used, and a numerical model based on quasi-steady state solution was developed. So these are the equations for solar energy, the calculation of solar energy, where some assumptions were made with regards to the absorbability of the solar panel and the efficiency of the heat exchangers and the thermal efficiency of the PVT panel itself. These are the borehole model details, how the heat extraction per borehole was calculated, and it was basically in the model, it was ensured that the borehole is able to meet the thermal demand of the system, and the equation at the end basically is sort of an energy balance where the energy stored in the borehole is on the left side, and on the right side there is the QPVT usable, which is the thermal energy gathered by the PVT panel, and the energy extracted from the borehole itself is subtracted from the total energy stored in the borehole. This is the heat pump model. So for the heating, in the heating mode, the condenser output temperature of 60 degrees Celsius was assumed for the hot water supply and space heating, and 5 degree Celsius pinch point temperature difference was assumed for the refrigerant in the evaporator and the antifreeze in the ground loop. So for the modeling of the system, as I mentioned earlier, the thermal load of a residential building, which was 3-bedroom terraced house in this case, was used, and solar irradiation of the location, which is Neathport Talbot in this case, was gathered from the weather station. This data was fed into the model as input, and also the thermal resistance of the borehole was calculated using the ground properties such as thickness, thermal conductivity of soil layers, and so on. And other parameters involved the undistributed ground temperature and borehole parameters. Based on these information, the energy gain from the PVT panel was measured, and also the heat energy extracted from the ground loop was calculated, and then the performance of the energy system, the heat pump itself, and the temperature variation in the ground was observed. So here is the thermal load and solar irradiation. The graph in the top shows the solar irradiance of a representative week in Neathport Talbot. The red trace represents the solar irradiance, and the thermal load profile during the week in summer. So while the blue trace illustrates them in the winter week. So the red trace is for the summer and the blue trace is for winter. The top graph shows the solar irradiance, and the bottom graph shows the thermal load for the residential building. So model inputs based on the real thermal demand of 3-bedroom terraced house in South Wales, which involved the space heating demand, cooling demand, space cooling demand, and hot water across seasonal conditions. And the orderly simulations were conducted using these conditions, representative summer and winter week conditions, to evaluate the system performance and ground temperature response. Here is the system performance analysis. So the summer borehole, the higher summer performance was observed for the PVT, as the PVC system performance varied seasonally, with some summer outputs reaching up to 3,500 kilojoule thermal and 450 watt electrical, which was nearly 3 times higher than winter due to greater solar irradiance and longer day hours. And it also showed the year-round flexibility during the low irradiance or overcast periods. The ground source heat pump system relied on subsurface heat, while sunny intervals enabled ground thermal recharging. So here the top graph shows the temperature of the working fluid coming out of the borehole, and the bottom graph shows the COP of the ground source heat pump system. Again, the blue trace is used for winter, and the red trace is used for summer. So the summer borehole outlet temperatures averaged around 13.8 degrees Celsius with minor fluctuations, while winter temperatures were lower, highlighting the need for solar assisted thermal recovery during colder months. Seasonal variation was observed for heat pump COP, which ranged between 5.4 to 5.55 in summer, and slightly higher on average in winter due to favorable ground conditions, which again emphasizes the importance of system tuning for optimal year-round performance. So next we look at ground temperature dynamics, that how it affected the temperature of the ground. So over the ground thermal imbalance showed a minimal deviation of less than 0.1 degree Celsius over a week, but a noticeable increase was observed over a month, which highlighted the cumulative effects of heat extraction and recharge cycles. Also, it showed that without effective ground recharge strategies, gradual temperature depletion can reduce ground source heat pump efficiency, and it can compromise system longevity. Here's a Sankey diagram which shows the energy flow between the PVT panels, ground heat exchangers, heat pump, and thermal load. So basically, the solar heat absorbed by the PVT is transferred to the ground heat exchanger. So some of it is converted into thermal energy, and some of it is converted into electrical energy, and some of it is lost as form of heat to the environment. Again, and then the energy extracted from the boreholes, it also is utilized through the ground heat exchangers, and this acts as the source for the heat pump, which is run by electrical energy and used to meet the thermal load of the residential building. Then the energy cost savings were compared. So integrating the PVT with again, the top graph is for winter, the bottom one is for summer, and the traces here, the red trace shows the system without PVT, which would be a conventional ground source heat pump system, and the green line shows a system which has a coupled PVT. Integrating the PVT with baseline ground source heat pump reduced the both peak and total electrical consumption, with PVT system providing thermal recharge and electricity generation. Weekly energy use decreased from 5.7 kilowatt hour to 0.43 kilowatt hour in winter, and in summer 29 kilowatt hour, from 29 kilowatt hour to around 4 kilowatt hour, which led to a household energy saving of 2.5 pounds for winter and around 11.5 pounds for summer. So next, we'll look at the limitations and scope for future work. So this was basically done as part of a feasibility analysis, which focused on modeling a site-specific PVT coupled ground source heat pump system, and it did not include any techno-economic analysis. And the future studies could look into more detailed techno-economic evaluation, looking at the capital expenditure cost, localized cost of energy, payback periods, and so on, and also comparative studies with other renewable systems like air source heat pump or standalone solar thermal systems can be investigated. And another tangent for future work is the developing control strategies and comparing the system with real world experimental tests to move beyond the design phase simulations towards the experimental validation and implementation. And finally, the conclusions. So the system was basically investigated was a PVT unit coupled with ground source heat pump system to develop to meet the space heating, cooling, and hot water demand for small community in South Wales. And the model results showed strong seasonal adaptability, energy efficiency, and stable ground temperature management, which supports the net zero goals defined by UK, achieving net zero by 2050, and also the local regional goals for decarbonization of energy. So other advantages of the evaluated or analyzed system are scalable modular design, which enables expansion to larger residential clusters and shared infrastructure. That's all from my side. Thank you for your attention. I would also like to highlight the I would also like to acknowledge the funding bodies which funded the project in which this work was done. So the mainly the project was funded by the Switch to Net Zero Buildings, and some of which was sponsored from by flexibility from cooling and storage. That's all from my side. Please let me know if there are any questions.
Thank you very much. Any question from the audience? I do. I actually like a lot your slide number 16. Maybe you can show it, please.
Yes.
I think at the end, when you live in Europe or these countries that you depend on heating mainly in winter, at the end, what matters is how much you pay.
Right.
And then I like a lot these cost savings. But I was wondering, why not to integrate another source of energy, like wind turbines or something, like to even have a higher saving.
Right.
Many times in these countries, when you don't have really a high sunlight in the winter time, but you have some other sources of. Actually, some of these places are very windy.
Yeah, that's a very nice suggestion, and actually, it is one of the comments that I got during the review process. That why haven't you investigated or compared this system with other renewable systems like a wind integrated system or air source heat pump systems? So this wasn't done as part of this work, and as you said that at the end, all that matters is the cost. So in the future work, we do aim to do a techno-economic evaluation. This is an ongoing project. So in the first part, we did a simple feasibility analysis. And in the next part, we will be looking at the techno-economic aspects where the integration of other systems, as you rightly mentioned, the wind energy system would be incorporated.
And another question, if I understood well, it's like you have this photovoltaic system at the central point where you had a heating pump and so on. Are you considering like to have photovoltaic systems in individual houses, like somehow like to share the initial cost and then to recover from the energy that they can produce and sell to the network?
So yeah, as I mentioned, that this is basically has a modular design, and the design of the system is such that, if I can go back to the schematic, so the idea is that each household will have separate PVT, and a separate
Okay.
heat pump. However, the ground heat exchanger will be shared. It would be a shared loop ground heat exchanger, which can meet the thermal demand of a small residential community, which can be any number of houses. So
Great.
each house will have a separate PVT and a separate heat pump.
Okay. Well, thank you very much. Thanks.
I cannot see you any hands raised, so please let me know if there is any other question. Otherwise, I'll stop sharing my screen now.
It is done. Thank you
Okay,
very much.
thank you.
We
Thank
don't
you.
have more questions. Neither time. Okay, thank you. Okay, our next talk is we got the person. Okay, the next talk has the title Design and Assembly of Vibration Measurement System for a Small Wind Turbine. And the speaker is Antonio Rodriguez. No.
Thank you. Hi, good afternoon. My name is Antonio Rodriguez Cruz. This work is design assembling of a vibration measurement system for a low wind turbine. Has content we have number 1 introduction, number 2 system description, number 3 experimental results, and finally conclusion and further works. Number 1 introduction. We know that the wind turbine system are the most efficient about the green energy system, ideally up to 59% efficient, ideally. But this system can be affected to the vibrations. With the time, some people observe that this phenomenon can be affect the system. And for example, in Castellani's paper, he shows that rotor imbalance in a wind turbine increase the vibrations. And in other paper, the author shows that in a programming simulation by ANSYS about the wind turbine, the most affected part are the blades. These blades are affected because the wind hit these blades, and this phenomenon produce vibration, and with the time produce fatigue too. So if we know or understand the wind turbines behavior, we need to obtain at least one of the 3 modal parameters. The 3 modal parameters are natural frequency, damping radio, and the deformation patterns. So if we can obtain at least the natural frequency, we can understand the wind system, wind turbines, the behavior about the system. So we assembled measurement system, and this system has one sensor and 2 smart boards. So how first step? Well, number 2 system description. This wind turbine system. Sorry. This system is Tecnológico de Pachuca. This system has 5 blades and nickel a tower. In this part,
The pointer doesn't work.
Okay. In this part, thank you. In this part, we put the sensor is an accelerometer, and in this part, we take the wind turbines behavior parameters. So, our first step, we need to obtain natural frequency in an analytical form. So, exist different mathematical methods. So we use generalize a single degree of freedom system. This method is a chain many degrees of freedom system to a single degree of freedom system. To when we use this method, we need to use this expression. This expression is the shape function. This function is necessary or is specific to use in tower systems. So with this expression, we can with this model of motion, we can find the natural frequency with the mass, damping, and stiffness generalized. This mass and damping are has a specific expression, mathematical expression. This expression are this. In this part, we use the shape function, and finally, we obtained this expression. This expression is the dynamic model generalized about wind turbine system. In this case, we neglecting viscous damping. Finally, we obtained the expression of natural frequency and in analytical format. With these parameters that we take of the wind turbine system, finally we found this natural frequency 2.36 hertz in this analytical natural frequency. So now number 3 experimental result. We assembled a measurement system, and this system has a sensor, which is an accelerometer, and 2 smart boards. These smart boards, when we put on top in the wind tower turbine, the wind turbine tower, this sensor send information or data to the first smart board. This smart board is an Arduino Due. This Arduino keep process change the analog signal to digital signal and send this information a second board. The second board is an Raspberry Pi 4. This board has a program created in Python code. This program change this information in graphic form. In this graphic form, we can obtain the natural frequency. This natural frequency is in experimental form. So this is the schematic diagram about the measurement system. Arduino, Raspberry, and this sensor is ADXL55 sensor. Well, in this part, we have a video. Can you put?
Can you play it, please?
Thank you. It's in Spanish, but in general, this video is about when we put on the top the tower the sensor, and we execute the program code in Python. And in this part in the time 1 minute 47 seconds, please. What? No, no problem. We can observe when the program is running. For example, in the sensor send information, and this program is processing this information, and when finish this program, this program show or display the graphic form. This program has some options. Kind of sensor in this moment only have one sensor, this accelerometer, and time and FFT. This FFT is about the fast Fourier transform. In this part is observed. Can you please pause? Okay, no problem. Thank you. Time sensor is a accelerometer in this case. Time, port, and FTT. And when the program were running, in this part I can see this part. So okay, can you 2, 3, and more. Yeah, it's okay. It's finished the program, and this part is show the graphic. The next okay. Thank you. So the program show this graphic. This graphic is about the acceleration measurement and timing of 53 seconds. This is the wind turbines behavior in the time domain. And in this graphic, shows the frequency. In this case, my analytical natural frequency is in some 1, 2, 4. That is in this table. 1 to 43 hertz, and in this case, we can obtain the natural frequency in experimental form. And finally, as a conclusion, the vibration measurement system is reliable in collecting, storing, and processing the data sent by the sensor. And second, all of this is graphical display using Python libraries. There exists a difference between natural, analytical, and experimental natural frequency. The reason is because the analytical natural frequency is obtained for a generalized single degree of freedom system method. This method is based to the cantilever beam principle. This principle is used to static system, and the wind turbine system is a dynamic system. So other reason is because, sorry, these parameters, are approximation in specific the tower mass and tower's diameter, because the wind turbine system is in operation, and it's very difficult get up and take this parameter. But these parameters are close to a real parameter. And finally, This work can be used as a basis for a future work, for example, remotely monitor a wind turbine. My reference it's all. Thank you for your time.
Thank you. We have time for questions. Questions?
Yeah, still well, did you find that is there an optimal place to hold your accelerometer in the wind turbine or anywhere?
Anywhere.
Okay. And the second one, do you consider it has the potential to build some kind of frequency catalog to prevent a stall in wind turbines? Yeah,
My election is very bad.
yeah, that your system can make some recordings, and these recordings you process, and you can have like a catalog of events. And in this, with this information, do you think that you could build a system to prevent the stalling in wind turbines? This phenomenon that is when your wind turbine loses stability and tends to fall.
The first, the objective, the final objective is a good idea, but the first only this work only is made monitor, remotely monitor about this system. But then the idea is that this system can be help to with other control to maybe break or show a signal to alert maybe to, for example, when this wind turbine is break or is have a strong work. Yes. So, but in this moment only is for monitor. Yes.
Thank you.
Yes.
Any other question? Please.
Some comment, the accelerometer has to be located in a position where you have to measure the first Mach shape because you're modeling the first Mach shape of the tower. So you cannot put anywhere the accelerometer. Okay, and have you performed some finite element analysis or experimental analysis with the complete structure, tower, boundary conditions, and the wind turbine? Because the dynamics is more complex when you consider the different elements. I mean, your model is only one single of the
Yes.
freedom. However, the boundary conditions, because looking at your boundary conditions, your connection to the ground is not symmetric.
Okay.
So you have a square with some screws. You have not symmetric performance, and on the top you have the wind turbine, and that wind turbine can rotate. So in different directions, you will have different components,
Okay.
different values for the first mode shape.
Okay. Okay. And this the beginner the sensor is collocated and is put in the only the tower. No, it's not. And this part is no problem. If this
Did you go?
yes, no. The measuring system is in the part the most no. Only the sensor, the accelerometer is in the top tower, but only the tower. The direction about of the move about the wind is no problem. There is no problem because this sensor is only in the tower. So, but in the next step is put other sensor, for example, sensor about the revolution per minute, and this sensor in my mind is put in the same place. No problem is the turn off the wind turbine. Yes, so in this case, the sensor and the system, measurement system is in the tower, only in the tower.
Well, we are on time, so we thank the speaker. Is it already connected? The next speaker, I think, is online. Okay, so the last presentation of this session on mechanical engineering and power electronics has the title Implementation of a Waste Heat Recovery System based on an Organic Rankine Cycle in a Cement Industry in Dominican Republic. The speaker, Rafael Batista. Can you hear us?
Yeah.
Hi.
Can you hear me?
Okay, great. You
Okay,
share your screen with us, please?
Yeah, I'm going to share my screen just to check that everything is okay.
Yeah.
Let me know if you can see it.
Not yet, but just wait a minute.
Okay.
Okay. Yes, now we can see it. So please
Okay.
go ahead.
Thank you. So let me know if everything is okay over there, and
Yes,
if you can
everything's
hear me
fine.
well. Okay, that's good. Then thank you so much for your attention and for the possibility of presenting this work titled Implementation of a Waste Heat Recovery System based on an Organic Rankine Cycle in a Cement Industry in Dominican Republic. This work was done by myself, Rafael Omar Batista Jorge, and Rubén Ramos Cipriano. I am from the Pontificia Universidad Católica Madre Maestra.
Rafael,
and Rubén
excuse
is
me,
from...
can you turn on your camera?
Oh, yeah. Give me a second,
Please. Thank you.
Okay.
Thanks.
Okay, give me a second. Okay. Now you can see me, right?
Okay, now share again your screen. Thank you.
Yeah, okay. So, Rubén Ramos Ciprián from Universidad Central del Este, Dominican Republic. This is the outline that we are going to develop today, the introduction, the problem statement, what is the literature review that motivates the contributions that we are proposing in this work, a little bit about the clinker production process, what is the system architecture that we have chosen, what is our experimental design, what results we have found, and what are the conclusions and future works regarding this project. Yeah. So first of all, in the context of Dominican Republic, we have a cement industry, and it's characterized, as in other parts of the world, by making an intensive use of energy in the production process of clinker, the main raw material of cement, right? As presented by Malul et al. In 2011, he did a research on what is the approximate power energy consumption per ton is between 110, 120 kilowatt hours per ton of clinker. So it's quite energy intensive, right? It's important to know that it is not only considering, this part is considering only electrical energy, because the main process also has some carbon process energy from fuel forces in the process, right? Currently, in the Dominican Republic, 7 companies dedicated to the manufacturing of cement. We are one of the main cement manufacturers in the area of the Caribbean, with a volume of 5.6 million metric tons in 2019. And it is clear that in order to reduce the energetic and climate impact of the cement industry, there is need for improving the efficiency of the cement industry, right? So this brings us to the problem. The clinker production offers a variety of possible low-quality heat sources for a waste heat recovery process, right? And they are a lot of heat sources, but they are of low temperature. And of course, they are qualified as a low-quality heat process. So typical Rankine cycles for waste heat recovery won't have much efficiency for capturing this waste heat, right? So selecting an optimal working fluid is challenging for low temperature recovery, requiring thermodynamic and environmental compatibility with industrial exhaust conditions. And there is also limited research and implementation of organic Rankine cycle system using our main working fluid for this study that is cyclopentane, right? Furthermore, the comparison of this fluid with other typical ORC working fluids in this setting is of importance. We did a little comparison regarding that. So this is a little bit of literature review. There has been previous works on WHR systems using organic rankine silicos in cement industry, but nevertheless, one of the main points for this study is that we are using two different sources of waste heat in the dual ORC configuration that we are proposing. Typically, in a dual ORC, what we do is that we have a second stream derived from a single point of heat source. In this case, we are using two heat sources from different processes of the cement production, right? So the main contributions of this work can be summarized as follows. A study of the cyclopentane as a working fluid for the fuel WHR system with low-quality heat sources, combining in a double ORC two low-quality heat sources for improving the power output of the system. Evaluation of the ORC cycle net power output using information from an actual cement plant in Dominican Republic. A little bit about the clinker production process, right? In here we have the main kiln for the production of clinker. This is the main heat source of the system. And here, typically they are burning here carbon. And then they produce between 1,200 Celsius centigrade here. But then we have the cooling tower and the alimentation tower. And then this is our primary source for the heat recovery process that are the gases coming from the feeding tower of the rotary kiln. Before going into the cooling tower, and this is the part on which this filtering process, so the particulates coming from the process, they can be discharged without hurting the environment. And also here we have the clinker. The clinker is coming very hot. Then we have a set of fans that they are blowing so they can cold the clinker before it goes to the cement silos for continuing the process, right, of cement production. So we have two possible sources of, in both cases, they are low quality heat sources under 300 Celsius degrees. So this is our main point of a study. So we propose two systems and we are comparing them. First, we are using a simple ORC system using our main study substance, cyclopentane, but we also use another kind of working fluids, and we have a comparison at the end. So in a moment, you're gonna see how those other fluids compare, right? And for the modeling, we are using a heat balance modeling and taking for reference each point of the process of the ORC to construct a modeling, right? Furthermore, this is the double ORC system. In here we have the gray cooler for the mass flow information of each item, the data sheet of the actual fans running this process was taken as a reference, right? And this is the heat balance modeling for each part. So for the clinkerization process in production, we have the kiln exhaust gases around the average temperatures around 240 degrees Celsius with an air mass flow around of 80 kilograms per second. And the clinker cooling stage around 220 degrees Celsius and with 50 kilograms per second of air mass flow. And regarding the cyclopentane as our main study fluid, it's important to note this is its thermal properties. It's as you can see from its boiling point, critical temperature is quite optimum for being used in this kind of processes, right? A low heat process. In only issue will be that it is highly flammable. So you may say, well, but you are using this highly flammable working fluid in this process. Just taking care or in consideration that in the cement industry, we have here carbon, which is highly flammable. Also here we are combining in some processes material that is highly flammable is working also at high temperature. So in this kind of process, it is common to have the combination of a highly flammable chemical with sources of heat. That is a reality in the cement production process. So it is important. It will be better if it was not that highly flammable, but it is possible to have this combination, and it is something common to call it like that in the cement process. Yeah. So data from a real cement Dominican cement plant was acquired using the SCADA system, and we take average values of those information from the SCADA. The data sheets of the fans was used for estimate average mass flow. The URC systems were simulated using MATLAB integrated with the open source CoolProd library. What we did was a heat balancing equation, solving it using the CoolProd library. And finally, the model introduced random variation heat source temperatures following a normal distribution to test the system robustness under real-world fluctuations. We take minimum and maximum values from the SCADA data, and then we introduce a normal distribution for adding some random noise to see how well the system behaves and how the actual electrical power production is affected by these variations, right? So for the fluid comparison, we use the simple ORC cycle. This is the MATLAB code in which we are using a CoolProd for fetching the properties of the various substances that we're testing. And then what we do is that we run the heat balance equations that were presented in the beginning. So in each point, we are doing the heat balance. And then, as you can see, water, the output power, if we're considering the turbine, right? This is the turbine in the output of the RRC, is quite low compared with cyclopentane and cyclohexane. Another types of reference, R134A and R245, are not capable, right, of producing positive output power with this configuration. Also, we are looking here at the effect of the Kinel-South gas temperature using, you see, this is the top production using the dual ORC system, right? This is the crate cooler temperature and the effect of the Kinel-South temperature, right? So we have a variation of almost 200 kilowatts regarding the variation between the crate cooler and the power output regarding the Kinel-South temperature. It is possible to have those variations. It depends also on the working points that are set up in the production. Sometimes you need a little bit less of heat because you have some hot spots on the kiln mechanical parts, so you reduce a little bit. So you can have those variations. It's normal. If we do an economical analysis from expected electrical energy production, there are some words that study the ERC's installation cost per kilowatt is almost $2,650. So if we are going to install a system of this size, more or less, is almost $9 million. But then we have modeling energy generation. Furthermore, considering the reality of the Dominican Republic, we are an island, so energy production is quite costly here. So that's why you see this is quite high compared with other countries, right? So we have a system lifetime of almost 20 years, estimated operation maintenance costs. So we have it's kind of a little internal rate of return, but nevertheless, we have a simple payback period time of almost 6 years. So the reality is that this is a viable, also a really option for improving energy efficiency of the cement production process, right? So the study confirmed that implementing an ORC system using cyclopentane as a working fluid is both technically and economically feasible for waste heat recovery in the Dominican cement industry. The dual ORC configuration, which utilizes both kiln and crate coolers as cases, presented the best configuration, right, with this top maximum production of energy. Also, the economic analysis fundamented that this is a viable solution for improving energy efficiency, right? And so also this provides a replicable framework for other kind of industries that are using or are producing low potential heat sources for waste heat resource, and taking advantage of things, right? So in future works, we are going to look how we can optimize even more the ORC system. Maybe we can use some sort of intelligence algorithms in order to explore automatically other kinds of fluids and in which conditions, for example, changing pressures, and for the supercritical, also consideration with supercritical mass and things like that, in order maybe to improve the performance. Testing hybrid solutions that combine the ORC with renewable sources is another point that we can explore. And also, we can refine the thermodynamic modeling to include non-ideal components, efficiencies, and branching operational behaviors. So thank you so much for your attention. This has been the presentation.
Very much. So I would like to have for some questions. Any questions from the audience? I have one. When you mentioned this payback on time, 5.8 years, how is it going to be affected by maintenance and the life cycle of the equipment? Because the cement process is a very highly aggressive process with materials and metals and so on.
In this case, I took into consideration the typical expenditures of maintenance, considering engineering, considering technical experts, also mostly also some parts change. So that's why I'm estimating $5,000 of maintenance cost. Maybe this can be a little bit more, a little bit less. The advantage in this case will be that as a closed cycle, and we are not interacting directly with the most, let's say that we don't have moving parts like just the pumps, maybe cleaning heat exchangers and things like that. So I think that this was based for the estimate operation of maintenance at cost. Considering, for example, we took as a reference the maintenance cost of cement mill. In more or less, this was the extrapolation that we did for assigning this value here, right?
Okay, we have an online question. Yes, please.
Yes. Hi, Rafael. Thank
Hi.
you for your presentation. I'm
you.
just curious that what was the thinking behind selecting these working fluids for ORC, and did you consider low GWP, zero ODP refrigerants, alternative refrigerants?
Okay. Initially, what we did was an initial exploration of typical working fluids that we find here in Dominican Republic. That was our first approach. So that's why we choose R134 and R245. For example, right now, what we are thinking of using R600 that is being also really utilized right now in our local industry. And then we look at the characteristics of the boiling point of the working fluids and the characteristics of the average temperatures of the exhaust gases. And then for that reason, we choose cyclopentane and cyclohexane for comparison. So that's what the main reason. Right now, and part of what we are planning on doing is instead of having this selection done manually, what we like to do is to ensemble some optimization algorithms with some restrictions, and then had a complete evaluation using the complete set of working fluids present in CoolProt in order to have an automatic selection process.
Are you aware of the GWP values of the refrigerants that you have considered? These 5 refrigerants.
If I have, sorry, I didn't hear.
The global warming potential number for these.
Okay, yeah. Regarding cyclopentane, global warming potential is under 10, and the ozone depletion is 0. The only problem with cyclopentane is its flammability.
Right.
Yeah,
Okay.
that's the main problem with cyclopentane. But as I told, the benefit of the cement industry is that they are accustomed to handling high flammable situations. So it won't be something out of their covering daily scope.
Okay, makes sense. Thank you.
Yeah.
Any question from the audience? I have one.
Mhm.
It seems like the goal of this work that you have done is like to find the
Mhm.
optimal working fluid. Then you
Yeah.
compare all these options.
Mhm.
But when you mention this idea of optimization at the end, do you mean the optimization of the operational process or ORC? What will be the parameters to be optimized, like the mass fluid rate? I don't know, pressure.
For example, what we have mass flow, they are fixed because that's the process, the maximum mass flow in each part. For example, but I can do something with the pressures. Maybe if I can have a little less pressure in one of the pumps here, for example. Oh, in this pump, maybe okay, I'm working on more 1 megapascal, but then maybe I can work with 900 kilopascal and have a better energy efficiency because then I am using less power on this water on this pump for elevating the pressure, right? So that's the idea. Doing some restrictions in order to have the optimal efficiency, setting up the pressures and maybe adjusting some temperatures and maybe also testing the working point of the fluids. So we can change the working fluid points of the fluids in order to choose the better work. For example, okay, I'm going to produce a little bit less energy, but then maybe I have a working fluid with better properties that cyclopentane, for example, with the flammability. So the idea is to make a automatic decision process using the whole database of CoolProp. Yeah, let's say that that's one of the main interesting points here, that with CoolProp, but you have to, I think they are like 200 working fluids over there. So if you can do all the evaluation automatically and have some performance index that you can optimize, it will be really nice to have that kind of optimization for automatic selection of working fluid.
Okay, well, thank you very much. So,
okay, thank you.
Okay, so with this, we finish this session on mechanical engineering and power electronic systems. So now we have the time for the closure of the Congress. So thank you very much for your assistance and have a nice afternoon. Thank you, Rafael.
Thank you, everyone. Bye.
Bye-bye. Thank you.